All right, let's talk about complex numbers. I know, you probably remember them from algebra class as that kind of weird x plus iy thing. But I'm telling you, there is a secret life to these numbers. A beautiful geometric life that can take really complicated problems and make them, well, incredibly simple.
So let me just start with a question. Imagine you've got a point on a graph, right? And you want to rotate it around the center, let's say by 45 degrees. How would you actually calculate its new coordinates?
Well, the way it's usually taught involves a ton of trigonometry. You're talking sines, cosines, these crazy angle sum formulas, and it all gets mashed together into, well, this monster of an equation. I mean, it works, don't get me wrong, but it is messy, it's clunky, and it is just begging for you to make a mistake somewhere.
And if you're looking at that thing and thinking, oh, come on, there has to be a better way, then you are 100% right. There is. And believe it or not, it's been hiding inside complex numbers this whole time.
Okay, so let's dive into this new perspective. To unlock this better way, all we have to do is just think about how we describe a point on a graph a little differently.
So here's the way we all learned first, right? Cartesian form. You describe a point by saying how far you go over on the x-axis and then how far you go up on the y-axis. It's basically like giving a street address. Go 3 blocks east, then 4 blocks north. Simple enough.
But there's another way. Polar form. Now, instead of over and up, you describe that exact same point by its direct distance from the center. We call that r, the modulus, and the angle of that line from the x-axis. We call that theta, the argument. It's a total shift in perspective.
And this really nails the difference. The Cartesian way asks, how far over, how far up? Just like a street address. But the polar way asks, how far away and in what direction? Like a compass bearing. You're getting to the exact same spot, but you're using a completely different set of directions to get there.
So, here's the crucial part. What happens when we use this new compass-bearing way of thinking to do math, specifically multiplication? This, my friends, is where the magic happens.
You can just forget about that huge trigonometric formula we saw earlier. The rule for multiplying two complex numbers when they're in polar form is, well, it's almost laughably simple.
That's it. Seriously, that is the entire rule. To multiply two numbers, you just multiply their distances from the center and you add their angles together. That's the whole thing.
And this right here, this is the big aha moment. That simple act of multiplying complex numbers in polar form isn't just algebra. It is a geometric instruction. It is literally telling you to rotate by an angle and scale the distance by a certain amount, all wrapped up in one single clean operation. Check out this perfect example. The number I itself, in polar form, its distance is 1 and its angle is 90 degrees. So what happens if you multiply any number by I? Well, according to the rule, you multiply its length by 1, so it stays the same, and you add 90 degrees to its angle. In other words, multiplying by I is a perfect 90-degree rotation. It's just beautiful.
So, if multiplication is just rotation, let's take it a step further. What do you think happens when you multiply a number by itself over and over and over again?
Well, think about it. Squaring a number, z squared, just means you apply the rule to itself. So you square its length, and you double its angle. Z cubed, you cube the length, you triple the angle. This is a famous idea called de Moivre's formula, and it basically turns exponents into super simple, predictable, repeated rotations.
Which, of course, leads to a really cool question. If taking a number to a power is like spinning it forward multiple times, what do you suppose finding a root is? Yeah, it's got to be the opposite, right? It's like asking the question, what number, when I rotate and scale it twice, lands me on this spot?
So let's take the number 1. You know, in the regular world of real numbers, the cube root of 1 is just 1. Kind of boring, right? But in the complex world, things are way more interesting. There isn't just one answer, there are actually 3 of them. And here they are. In the complex plane, the number 1 has 3 totally different cube roots. I mean, sure, there's the obvious one over at an angle of 0, but there's also one sitting at 120 degrees and another one at 240 degrees. And why? Because if you take that 120-degree number and rotate it 3 times, you do a full 360-degree spin and land right back at 1. See? It's all geometry.
Okay, so we've seen how simple math operations can turn into these powerful geometric actions. But it actually gets even cooler.
We can use complex numbers to write equations that literally draw shapes for us. Take a look at this equation. It looks so simple. Those vertical bars, they just mean distance. So this equation literally reads out loud as the distance between any point z and some center point z0 is always equal to a constant number, rho. And what is the definition of a circle? It's exactly that. A timely piece of algebra draws a perfect circle.
Or how about this one? This says, the distance from our point z to some other point z1 is always equal to the distance from z to a different point z2. Now just think about that for a second. What is the set of all points that are an equal distance from two other points? It's a straight line, right? The perpendicular bisector between them. Once again, a super simple equation describes a fundamental geometric shape.
So, the real takeaway here is pretty profound. These numbers, these z equals x plus I things, they aren't just some abstract concept from algebra class. When you learn to see them through the lens of polar coordinates, they become this incredibly powerful and elegant language for describing geometry, rotation, and the shapes of the world around us.
Which really just leaves us with one final thought to chew on. If something as basic as rotation can be simplified this much using this language, what else can it describe? And it turns out, the answer is a lot. From the alternating current buzzing in our walls to the weird oscillations of quantum mechanics, this geometric language of complex numbers is absolutely everywhere. So the question is, what else might it be describing that we haven't even figured out yet?